Because of the very small sizes of atoms and molecules compared to large macroscopic objects, it is very common to assume that atoms and molecules are point particles that have no volume and no radius. Now, if this was actually true, if molecules were in fact point particles with zero radius and zero volume, then that would imply that collisions do not take place on the subatomic level. And that's because if they have no volume, then molecules are invisible to one another. But we know this is not actually true because collisions on the subatomic level between two or more different molecules or atoms do in fact take place. And we define something called the mean free path given by the L with the M symbol on the bottom as the average distance that a molecule or atom travels before it makes a collision with another atom or molecule. So, let's suppose we have the following blue molecule that is traveling along a straight path with some velocity. So let's suppose it moves this distance given by d1 before it makes its first collision. It collides and then it moves in a different direction with a different velocity. Let's suppose now it travels a distance d2 before it makes its second collision. Then it travels a distance d3. Now, if we want to find the average distance, we simply find the entire distance the molecule traveled and divide it by the number of collisions. So let's suppose we want to calculate the mean free path over this distance. So d1 plus d2 plus d3 divided by the number of collisions, in this case 1, 2, 3 collisions. And that would give us the mean free path. Now, generally speaking, what is the equation that gives us the mean free path? So let's determine the mean free path given by L with the M subscript on top. That stands for mean free path. So, let's suppose we have a certain container, and inside this container we have n number of total molecules. And let's suppose that the volume of our container is given by V. So n is the number of molecules and V is the volume of our container. Then we define the concentration of molecules within our container by the following equation. So the total number of molecules divided by the volume gives us the concentration of our molecules. It's the ratio of the molecules to the volume. Now let's suppose we want to examine a very small cross-section of our container. Let's suppose we want to examine the following cylindrical shape. So let's suppose we begin with a certain molecule shown on the left that is traveling with the velocity given by V with the bar symbol on top. So the molecule on the left moves to the right with an average speed given by V with the bar symbol on top. And we assume the other molecules within this region are stationary. So as this molecule moves with the velocity, it collides with the other molecules. Let's suppose the radius of each of our molecule is the same. It's given to be r. And let's suppose the radius of this cylindrical piece is given by 2 times r. So if the distance of this entire pipe, if this entire distance is given by d, well then that distance d is equal to the velocity of our particle multiplied by the total time elapsed given by delta t. So delta t, the total time elapsed, multiplied by the velocity v bar is equal to this distance d. We'll need to use this in just a moment. So let's suppose we want to calculate the number of collisions that take place as our molecule moves along the following horizontal axis. So the number of collisions within the cylinder is simply the concentration of our molecules multiplied by the volume of this region. So our concentration is given by N divided by V, and we multiply by the volume of the cylinder. Now, the volume of the cylinder is simply the cross-sectional area of that cylinder multiplied by this distance, where the distance is this value here, the product of the time and the velocity. So N divided by V, our concentration of molecules multiplied by pi times 2r squared, where 2r is the radius, multiplied by the distance, V bar multiplied by change in t. Now earlier we said that the mean free path is simply the total distance traveled divided by the number of collisions. So the total distance traveled between this point and this point is this quantity. So V bar multiplied by delta t. And we divide that by the number of collisions, which was calculated in this portion. So notice these will cancel, and we're left with 1 divided by 4 pi r squared multiplied by N divided by V, where N is the number of molecules in our entire container, V is the volume of the entire container, and R is the radius of our molecule, and pi is simply a constant. Now, this is the equation that gives us the mean free path as long as the other molecules are not moving. But what if these molecules are in fact moving? Well, if these molecules moving, then we have to use not the average velocity in this case, but the relative velocity. So this becomes a relative velocity. And because the relative velocity is equal to radical 2 times the average velocity, we get the following result. So we plug this into the bottom and we get the following equation. 1 divided by 4 pi times radical 2 times r squared multiplied by N divided by V. This is the equation that gives us the mean free path, assuming that the other molecules within our container are in fact moving. So we have two different equations. One equation works as long as we assume that these molecules are stationary, but if they're moving, we have to use this equation.